We move on from things being congruent to things being similar in this chapter. But before we can talk about similarity, this first section lays the groundwork needed first. The first part of this groundwork is the ratio, which many of you have probably worked with before. Officially, a ratio is a comparison between two quantities. Let's look at an example. I happened to be working with concrete this weekend. On the bag of my quick setting concrete mix, there were these instructions. Add 4 parts mix to 1 part water. That's simply a ratio. It is a comparison of two numbers. It tells me that a successful mixture will include 4 times as much mix as water. Note that there are no specific amounts listed. This isn't like a recipe where it is telling you how much of each to use. It's a ratio, a comparison instead. If you had 4 gallons of mix, you would need to add 1 gallon of water to make the correct mixture. If you have 4 cups of mix, you would need to add 1 cup of water to have the correct result. The ratio doesn't care how much mix you use. A ratio is simply comparing the relative sizes of two things, not how much either thing is. There are many ways that you can write a ratio. In the last example, we had a ratio of 4 parts mix to 1 part water. That can be simplified down to simply 4 to 1. That is one way to write a ratio, but it is not the only way. If you want to compare x to y, then you have 3 possible ways to write it. The first is to use English like I have already done and say x to y. You can use colon notation and do it like this. Or the last option is you can write it as a fraction like this. Those are the 3 ways that you can write a ratio. Note that dividing by 0 is still a big no-no, so y can't be 0. One of the ways to write these ratios is as fractions. You probably had it drilled into you back in your fraction days that you always needed to reduce your answer. The same is true of ratios. If you have a ratio written as a fraction, students almost always remember to reduce. The 6/8 gets reduced down to 3/4. However, you must always reduce your ratios no matter how you write them. If you write your ratio in English, the 6 to 8 needs to reduce down to 3 to 4. If you go with colon notation, the 6 to 8 also reduces down to 3 to 4. It doesn't matter which method of writing ratios you go with, you should always reduce them down. Since most students naturally remember to do that with fractions, and you usually have your choice which method of writing them down you want to use, many students opt to use the fraction method when they can, so that they don't forget to reduce their answer. One last thing with these ratios which can be tricky. What happens if you have a ratio of 15/3? With your normal reducing fractions rule, you would reduce it down to a 5. However, that would be incorrect here. Why? What should you do instead? The official definition of a ratio clearly says that it is a comparison of two quantities, and 5 is not two quantities. It is only one. So in this case, you should reduce down to 5 to 1, not simply 5. 5/1 is a valid comparison of two numbers. On a map, there is often a legend which tells you the ratio that is in use. It might say something like 1 inch to 50 miles. So on this map, 1 inch represents 50 miles in the real world. What is the ratio of that legend? And the ratio is definitely not 1 to 50. This is a typical math problem in this section, and it is one of the most commonly missed questions, so you have to be careful. You have to convert the units first before you can come up with your answer. It can be easily missed, especially when students are rushing and not reading carefully. But that wouldn't be you, right? Oh no, definitely not you. It's easy to miss, so be careful. We need to convert the ratio into similar units. If you do the calculation, you will find that 50 miles is equal to 3,168,000 inches. So the scale on the map is really 1 inch to 3,168,000 inches. However, we are not done yet. If I rewrite our ratio as a fraction, it will become more obvious. You may have done this before, especially in science class, but the units end up canceling each other out. And yes, you are allowed to cancel out units. Your final answer for the correct ratio on that map is 1/3,168,000. Note that the ratios will almost never have units in the final answer. Units almost always cancel away. There are only a few instances where it makes sense to have different units. A map legend happens to be one of them. What intuitively makes more sense to you? 1 inch representing 50 miles, or that the ratio is 1/3,168,000? That's why map legends are often in different units. But it's one of the very rare cases. Almost always, your ratios will be in the same units. This is still one of the most commonly missed pieces from this section though, so be careful. Read carefully. If the units are different, you will need to convert them to the same thing so that they will cancel each other away. Now we get to an extended ratio. If a ratio compares two numbers, what do you suppose an extended ratio is? An extended ratio compares 3 or more numbers, like x to y to z. In this extended ratio here, the ratio of the first two numbers is x to y. The ratio of the last two numbers is y to z. And the ratio of the first and last numbers is x to z. It is sometimes helpful to break it down into smaller pieces like this, but actually, most of the time, you will just keep the whole extended ratio x to y to z. For example, gunpowder has 3 ingredients: potassium nitrate, charcoal, and sulfur. In order to get a good reaction, you need to mix the ingredients in the ratio of 10 parts potassium nitrate to 8 parts charcoal to 3 parts sulfur. It's an extended ratio of 10 to 8 to 3. Note that modern firearms don't actually use gunpowder anymore. They use what is known as smokeless powder, which isn't truly smokeless, but it's far better. The original gunpowder had 2 major drawbacks. It made a holy mess, and it uses quite a bit of sulfur. If you don't know what sulfur smells like, think rotten eggs. So imagine old battlefields, coated in black residue, and smelling of rotten eggs. Not to mention all the bloodshed. Fun times. The gunpowder ratio is 10 to 8 to 3. Just like regular ratios, you can avoid writing the 2's, since clearly that is a lot of writing and might cramp your hand. So you can use colon notation instead. Well, what about writing it as a fraction? Should you write it with a larger fraction bar on top, a larger fraction bar on the bottom, all fraction bars the same size? What do you think? Generally speaking, you don't write extended ratios as fractions at all for this very reason. You should use English or colon notation. Of the 3 choices below, the third one with the equal length fraction bars is the most correct, but still, you just don't do it. It confuses people. Fraction notation is fine for a regular ratio, but is generally not used for extended ratios. Time for a quick example, as this is a very typical problem for this section. The angles of a triangle are in the ratio of 3 to 7 to 8. What is the measure of each angle? When you look at an extended ratio like this, you need to realize that I can multiply each of the numbers in the ratio by the same number and maintain the ratio. If I multiply each of them by 2, then I end up with 6 to 14 to 16. That's still in the right ratio, just not simplified. If I multiply the original ratio by 3, then I end up with 18 to 21 to 24. Again, those numbers are still in the right ratio. It is important to realize that as long as you multiply each number in the ratio by the same thing, you are okay. So, you can do 3x to 7x to 8x. No matter what the value of x is, you have the correct ratio. Our goal for this problem is to figure out what x needs to be in order to solve our problem. We know that the angles of a triangle add up to 180 degrees, so we can write this equation. Then simply solve. This gets us down to x equal 10. However, we aren't done yet. Students will often just quit here since they found x. But the question didn't ask for x. It asked for the measures of the 3 angles. So you need to plug x back into the 3x, the 7x, and the 8x to get the final answer. 30 degrees, 70 degrees, and 80 degrees. You can quickly verify that those are in the correct ratio, and that they also add up to 180 degrees. This is a very typical problem from this section. A proportion is an equation stating that 2 ratios are equal. Up until now, we have just dealt with comparisons of 2 or more things. We haven't set anything equal. We haven't had an equation. And math class often deals with equations. You might have noticed. But we haven't had an equation yet, until now. If I write out a proportion in English, it looks like an old SAT analogy question. 10 is to 6 as 5 is to 3. That doesn't look very appealing. We can use colon notation instead and have it look like this. Clearly that is a step up, and preferable to that English abomination. But by far the most common, since you have worked with things that look like this before, is to use fraction notation. That is probably the most comfortable way of the bunch, but theoretically you can use the other methods if you prefer. No matter how you write it though, these are proportions. They are saying that 2 ratios are equivalent. There are also extended proportions. You can probably guess what they are. If a proportion sets 2 ratios equal to each other, an extended proportion is an equation stating that 3 or more ratios are equal. Just like the regular proportions, there are multiple ways that you can write them out. You could use English, A is to B as C is to D as E is to F. I have to say, if English words were ugly with a proportion, this looks particularly ugly. Sorry, I guess I will hate away. This looks like a brutal way to choose. You could opt for colon notation. This certainly looks better. But just like the regular proportion, for most people fraction notation is the best way to go and is clearest to people. But you can certainly choose which method you like best. Now that we have proportions, you can manipulate proportions in many different ways and still end up with a valid equation. This is often going to be very handy. It is going to be most useful when we get to section 7.5. There are 4 properties of proportions that we will be going through. The first one you probably have done before. You likely have seen a problem like this before. When presented with this previously, what did you do to solve it? Most students are taught to cross-multiply to solve it. You end up with 4x equals 60, and thus x equals 15. That is the first property of proportions. We can generalize it a bit. If you take a proportion like this and cross-multiply it to get WZ is equal to XY, that is known as the cross products property. Let's start with the same generalized proportion. The second property of proportions we are covering is that you are allowed to flip the fractions upside down. Let's put in some actual numbers so you can see what happened. Instead of my proportion with variables as terms, here I have filled it in with some numbers. You should be able to quickly see that the proportion is true. Both sides of the equation reduce down to 4/7. This second property of proportion says that I can flip the fractions so that this proportion can be rewritten as 7/4 equals 21/12. Doing a quick check of that new proportion shows that both sides do, in fact, reduce down to the same thing. 7/4. It is important to note that the new equations we are writing due to these properties of proportions are not actually equivalent proportions to the original. They are just valid ones. The top proportion reduces down to 4/7 on both sides. The bottom one reduces down to 7/4 on both sides. Clearly those are not the same. It's just that this property of proportions lets me write a new proportion, which is valid. Both sides of the equation are equal. But wait, there's more! I know you're excited. This is the third property of proportions we are covering. We'll start with that same proportion. This third property says that you can make a fraction out of the numerators and a fraction out of the denominators, and they end up being equal. So in my proportion here, the numerators are w and y. I can make a fraction out of these two. The denominators of my original proportion are x and z. I can make a fraction out of these two also. You will notice that when I made my fractions, I went left to right both times. W first, then y, left to right. Or for the other one, x to z, left to right also. You can actually go the other way if you want to. This time I am working from right to left instead. This also makes a valid equation. You'll notice that the right to left one is just the left to right one flipped upside down. And the second property of proportion said we can do that. So it doesn't matter which way you go, left to right or right to left. You just have to make sure you do the same way for both fractions. Let's put in some actual numbers so you can see what happened. Here's the proportion you should be used to seeing by now. We can make a new fraction out of the numerators and a new fraction out of the denominators. If I work from left to right, then my proportion can be rewritten as 4/12 is equal to 7/21. But that's only one possibility. If I work from right to left, then I end up with 12/4 is equal to 21/7. Both of them work. The left one reduces down to 1/3 on both sides. The right one reduces down to 3/1 on both sides. That works. You can go either way. But be careful that you go the same direction both times, otherwise you might get something like this, which clearly doesn't work. Pick a direction and stick with it. Our fourth and last property of proportions is a little more esoteric, your vocabulary word for the section. We start off with the same proportion, but this last property says that you can add the denominators of both sides to the numerators. Now this may seem a little odd, but what you are actually doing here is adding 1 to both sides of the equation. It helps a bit to see that if I rewrite it like this. Adding the denominators to both sides is simply adding 1 to both sides of an equation, which is certainly allowable. Once again, let's put in some actual numbers so you can see what happens. And once again, here is our familiar proportion. Welcome back. This property of proportion says that we can add the denominators to both sides, so my proportion can be rewritten as 4 + 7/7 equals 12 + 21/21, which simplifies down to 11/7 equals 33/21, and that works. Remember, all this property is doing is adding 1 to both sides, but you have to be very careful. I need to give a huge warning here. This property of proportions is by far the one students most commonly use improperly. Here's the problem. You have been drilled into you, or at least you should have been drilled into you, that if you do one thing to one side of an equation, you must do the same thing to the other side of the equation, which is absolutely true and fine. Here's where students get tripped up. They start the problem, and they have added the denominator on the left to the top. They have added 7 to the top. So when they work on the right side, they try and make sure they do the same thing, so they add 7 to the top there too. That doesn't work. It seems to the student that they have done the same thing to both sides of the equation, but they haven't. They have added 7/7 on the left side of the equation, but only 7/21 on the right side of the equation. That doesn't work. When they simplify, they get 11/7 equals 19/21, which isn't right. You just need to be careful here. I have seen it a lot. Students make the same mistake over and over. Don't fall into that same trap. Make sure you add the denominators of both sides to the top.